my computer for the logic analyzer. And what we're going to do next is, let me, there we go. Okay, cool. Do that here. So I'm going to bring up the software on the other side of the screen here for us. And the first one we're going to look at is PulseView. So I just want to kind of give you just a quick little demo of what some of this looks like. So as you can see here, shift that way. We have everything hooked up on this side of the house. Remember, we have UART. So RX, TX hooked up to this based off the pinout that we found online. And of course, ground's hooked up as well. We followed the mappings here. So we're going to kind of take a white box approach with this, and let's just assume that we know everything already. So let's assume that we found the data sheet for the device that we want to kind of probe and take a look at. What we want to do next is from the software here, I'll give you a quick little run through. So we'll go back to full screen. This is the SIGROC PulseView. So with the PulseView, you can select the device that you have plugged into your computer. In this particular one, the driver that we need is the FX2 LAFW. So we'll select that from the dropdown, and we'll click scan for devices using the driver above, and then we'll click OK. And that basically has it hooked up. So what happens here, there's an airplane flying above here, so you might be able to hear some background of that. What you see here is that there's 8 channels starting at 0 and ending at 7. So that's representing the 8 channels that the logic analyzer has. Remember, it's 0 through 7 on the logic analyzer. What we can do is we can lower that because we're only using RX and TX. Ground is assumed. You're always going to use ground. So we want to select D0 and D1. So we're going to remove some of these other guys here. Going back to the software here, you can change the amount of sampling that it does. In this particular case, I have it set at 1 millisamples per second. So that's the setting for that. And we'll talk about that a little bit more whenever we get into Saleae software. But the cheaper logic analyzers can sample at a slower rate than the Saleae. So there's a little bit of a limitation here. And here's the speeds as well. So we're going to stick 20 kilohertz. So let's just plug the sucker in. Let's just see what happens, right? So I'm going to hit the power button. We're going to see the lights come on the Raspberry Pi right here. And then I'm going to hit the run button. Whoopsie daisy. Stop. Let's try that again. And then we can click this button here, which makes us keep up kind of with the timing of the actual logic analysis that's taking place. So we'll see kind of some spikes and voltages as things kind of happen. Again, this is over UART. So think of like the TTY connection over some type of serial or SSH interface. Imagine just the boot up of a Raspberry Pi. So it's just going to do its crap. And then at the end, it's going to be like, okay, Raspberry login type stuff. So we'll go ahead and stop it now that we're getting kind of closer towards the end here. Yeah, that's the last one. So if we take a look here, this is basically the capture. I captured for, as you can see, 35 seconds. So the thing about this, let's go ahead and go back into full screen. We don't really need the camera so much right now, but we'll go ahead and expand everything back out. And let's just take a look over here because this is let's just pretend again, let's just assume that we know the answer to this. This is basically where it's just prompting for a login for the UART interface. So we'll go in here and we'll kind of scroll. And even if you were unsure of which one was RX or TX, you could pretty well assume, if you at least knew that these two connections were UART, that this one's going to be TX and this one's going to be RX. How is that? Because TX is sending us data and RX is literally a flat line. So a couple of things there that can kind of help you out. And one other thing too is that this particular software does have protocol debuggers. So let's take a look at that. Let's go ahead and remember we set TX to D0 and we set RX to D1. So another thing too, we already have 115200. We're going to keep everything else basically default here. The least significant bit first is correct. We'll switch that to ASCII, and we'll come in here, and then it should do some decoding for us. See here, usually it takes a second. See if she works here. Yeah, so again, just a high level example of the protocol decoding available for this particular PulseView software, and some of the stuff you can do. So it recognizes stop bits, it recognizes frame errors, break conditions, things like that. Now, what I want to also do real quick, let's just exit completely out of here. We don't want to save. Another thing too is it's pretty nifty. PulseView has SIGROC. They have like their own proprietary format where you can like save your data and then like import it into Saleae or other. You can manipulate it also from like the command line. We want to now switch over to the Logic software from Saleae. So Saleae has their own set of software. They actually have two sets of software that we're going to review. And what I want to do is open it up here. And what I want to do is show you guys both sets of software to kind of show you the epicness of what it has the capability of doing. So on the left-hand side here, we have the Saleae Logic 1.0, 1.2.18 software, I guess technically. And in this particular case, it's very similar. So remember, here's all the 8 channels, and that's pretty much the situation that we're looking at. Mind you, remember, this is all digital signaling, so there's no actual analog signals going on in this particular case. So very similar to the other software, you can do the same protocol analysis. So we have, for instance, async serial, which is UART. And UART is an async serial communication protocol with I2C and SPI. So there's a whole list of different protocols supported also by the Saleae software. Your decoded protocols, it can actually decode also. As we saw earlier with the other software, it decoded it, but it's kind of limited on the amount of information that it can present to you. The command line is where the SIGROC software is very strong compared to Saleae. There's also annotation. So with the annotations, you can kind of capture during periods of time. But the thing I want to show you guys the most here is with logic analyzers. It's not specific to Saleae, but let's just go ahead and power this guy off. So as you can see on the right-hand side of the screen, the light's now off on the Raspberry Pi. Let's go ahead and power it back on. But also we're capturing for 30 seconds. Let's just stick to 4 mega samples per second. And then we'll go ahead and power the sucker back on and we'll let it start. So as you can see right here, the only sad panda part about the Saleae software is that it doesn't like live view show like the results of what's going on with everything. So you're kind of stuck with like just this kind of boring screen here. So you can't really see the sort of interactive, like, oh, here's like, the waveforms and whatnot. But whatever, it's all good. We'll go over some the 2.0 version of it where it does offer some sexier GUI stuff. So here's the output of our capture. So let's scroll out and we can see very similar to the PulseView, take this full screen, that there was actually some data captured here, very similar to what we saw earlier. Now let's scroll in, and as we talked about earlier, remember channel 0 is the TX line of the Raspberry Pi. So of course we're gonna see data. Now, a couple things is that let's say we wanna add a protocol debugger, just like what we did with the PulseView. Let's go ahead and add this. We'll say channel 0 is serial, that's the TX channel, and let's click auto Baud, right? So let's pretend for a second that we do not even know the baud rate of this device. Let's pretend that we actually think that it's UART, but we actually don't know if it's TX or RX. We've already actually kind of figured out that it's TX because remember channel 0, we're seeing data, it's transmitting data to us. RX is a flat line because we're not sending any data back. So we do not know the baud rate. Let's just pretend like we want to open up like a screen session or some type of like a serial session with the device over TTY serial, but we do not know the actual bit rate of that serial connection. So we'll just leave it at default 9600. We'll click this little checkbox here, auto Baud. We'll keep everything else default as well. This is all pretty standard for a normal serial interface on an embedded system. We'll click save. We now see the async serial is here in this corner. And kind of a cool little thing you can do also to help you figure out that baud rate. This is pretty neat. Now earlier, I'm gonna bring this up for you guys real quick. In the actual slide presentation, I had this little table here that showed the actual microseconds as well as the baud rate in this table. So if it's 833 microseconds, it's a 1200 the bit rate is 1200. If it's 52 microseconds, it's 19200. If it's 8 microseconds, it's 115200. Now, if we go back here, what we can actually do is we see the actual, let's take a look here, the waveform. So from where the actual rising edge to a falling edge of one complete uniform wave. Here we go. This is a good one. It's super tiny, but I hope you guys can see that. 8.5 microseconds. It's pretty nifty because that basically tells us what the baud rate is without us even having to like measure the baud rate. So if we, go back to our table here, remember 8.5? 8.5 is what it measured as the baud rate. We look here, and 8 microseconds is 115200. Remember, digital is never going to be 100% accurate. It's going to do its best at that representation. Also, there's latency in the cable. There's latency in USB 2.0. In this case, this is one of the cheaper logic analyzers. We're using USB 2.0. So either way, it's not going to be 100% accurate. It's going to be like slightly off, but it's safe to assume that it's closest to that number than it is to any of these other numbers. So that being said, let's just do something a little wacky here and just enjoy the luxurious features of the Saleae software. So I just lowered the sample time to 5 seconds. Remember, if we go back here to the settings, we have it set. Let's just see it automatically detect. It's already changed, but let's just put it back to 9600. Imagine this is like a fresh scan. So we'll power the device off, and then we'll power the sucker back on, and then we'll go ahead and start sampling. So based off of the sample rate, the Saleae software is smart enough to realize what that particular baud rate is. In this case, it already converted to us. While that is not the actual bit rate, even though that would probably work, it's 115200. It's close enough for what we're trying to do here. So let's take it a step further, and then let's switch this back over to 30 seconds. And let's power it off, and then let's power it back on again. Now that we know our baud rate, let's just see what it can do. And let's make it full screen because we all know what a Raspberry Pi looks like. I can't make it full screen. I'm gonna sit here and just stare at this thing boot up.
So while we're having a little break, let me ask you one of the questions. So I have a question here. Is the Saleae or the PulseView logic analyzer software free and open source? How would you go about downloading or purchasing those?
The Saleae software, it is actually free. It is not open source, however. It's free. You can download it straight from their website. You can't compile it because again, it's not open source, but it's 100% free. You don't have to spend a dime for it. However, the SIGROC, so the PulseView software, I believe the GUI is open source. 100%. I know the SIGROC CLI is open source because I just compiled it actually like 2 hours ago. But yeah, so the Saleae Logic free, not open source. SIGROC PulseView, 100% free, maybe open source. SIGROC CLI free and open source. And taking a peek here real quick, we can see in the decoded protocol section here that we actually have the output of what we saw over the UART interface. So under voltage, it's kind of printed funky here, but that's the actual output of what it's seeing. We had it set to the ASCII. So the output is being displayed in ASCII format. So kind of neat. You can see all that kind of stuff. Scrolling even further down here, we have like, detected, blah, blah, blah. But go to the very bottom. Maybe we missed it, but it would even capture, yep, there we go, like Raspberry Pi login. And that's basically on the UART connection, waiting for the, the typical Pi, password Raspberry, because no one ever changes their default on that. So anyways, as for that particular demonstration, that's pretty much it. And, kind of continuing on with that particular question that was asked regarding the free and open source nature, are there any other questions, I guess, up until now?
Yeah, I have just one more for you. What is the max number of logic analyzer channels needed for most IoT situations?
That's a good question. And I'll be perfectly honest, like I rarely run into an instance, and I do this, I'm not like hacking on IoT like full time with my day job. Again, I'm a pen tester, but I do it a lot, just kind of as a hobbyist as well as just kind of as a side type thing. There's very rare instances that I've run into a situation where I needed more than 8 channels. So in cases that I've ever used these logic analyzers, it's mostly been on 3 different protocols: UART, SPI, and I2C. And none of those 3, protocols really require more than 8 channels. Now, I don't want to say it wouldn't be necessary, but I would say that it's kind of a low likelihood that if you're trying to get started as like a hobbyist, that you'll actually need more than 8 channels. And all of the devices that we're working with here support 8 channels. You can buy them up to like, shoot, I don't even know. I know Morgan on our team has the big one. I think it's 6. Is it 16 channels? Is that their biggest, or is it the?
I think it is 16. Yeah,
16.
I think
Yeah,
16 is the biggest.
The big boy. And I don't know that I would like have a need. However, it would be super handy to have in case I ever did have that need. But I would probably err on the side of saying that it's likely that 8 channels would be good enough for you.
Okay. Yeah. No more questions yet.
Cool. So speaking of which, UART, SPI, and I2C, how do they function? So as we saw earlier, UART's an asynchronous connection. So what that actually means is that there's no clock on either side of the connection controlling the actual rate that data is being transferred. It's an agreed upon number where you're supposed to actually know. So the bit rate and the baud rate is important for that. How it determines the actual connection speeds also is it uses parity bits. So there's basically another layer of overhead that's being sent over the line of communication so that the negotiation and the actual transfer of data can take place. With SPI and I2C, they're actually synchronous, meaning there is a clock that's determining the communication time. So for instance, SPI operates on a slave master model. So the master is the actual determination of the clock speed. That's the one with the actual crystal that's going to determine how quickly data is going to be sent. The slave is going to basically accept that at that particular rate. And that number is negotiated throughout the process. I2C functions in a very similar way. Moving on to the actual interfaces associated with these 3 different protocols. Again, UART has 2 channels. Again, this is the channels column here is assuming that ground's hooked up. So disregard ground right now. This is only the data lines and the information communication lines that's taking place that we're really concerned with here. That's RX and TX for UART. SPI has 4 channels. That's going to be MISO, MOSI, CS, and clock. Chip select is enable, and clock is, again, the determination of how quickly that data is going to be sent and received. MISO and MOSI are a little bit like interchangeable. It can just depend on the situation that's going on. So with SPI specifically, remember there's master slave. The master will send out data to the slave over MOSI. That stands for master out, slave in. The master will receive data from the slave over master in, slave out. The master will determine the clock rate, and the chip select is the enable. So the chip select is only applicable whenever there's multiple slaves communicating with a master. And then I2C is pretty simple. It's SDA and SCL. SCL is the communication for the determination of how quickly data is to be sent and received, and SDA is the actual data line. So moving on from that is I guess, are there any questions maybe with regard to SPI, those 2 protocols, with how they apply maybe to logic analyzers? Maybe not, because I know we just kind of just answered some questions.
I'm sorry, I was kind of muted. Currently, we don't have any questions specifically on this, but I do want to encourage people that are in the actual channel as attendees. Please think of questions and post them into the Q&A session. Okay, you can move on, Jonathan.
Cool. Yeah, I think we had a disabled chat because we had some flattering comments earlier that was kind of awesome. The first, I think Sam was mentioning it was one of the first issues we had run into with something exciting here. But anyways, okay, so let's move on to the first exercise. No, guys, yeah. So let's move on to the first exercise here. Actually, I'm gonna skip the first exercise and let's move on to the second one because we just looked at UART. Let's look at something fun. Switch it over to SPI. Also, I want to show you the sexiness of this new Saleae software as well. And let's bring up the new hotness here. I didn't know that Saleae had released this this new software. I think it was Morgan. So Morgan's our lab manager here at Rapid7. I think it was either he or Daryl that had pointed this one out, but Daryl showed me some freaking sweet new features that are basically have to do with this new software. So like, just to give you the quick rundown here, we still have, I'm sorry for shifting this screen around and stuff, but remember, we still have the old school, not the old school, the cheaper end logic analyzer hooked up. We're about to switch over to Saleae though. I want to show you guys some other stuff. So this is the new Saleae Logic 2 software. So we're now at 2, and you can change the amount of channels, of course, that are hooked up here. You can change, like, you know, the different protocol analyzers associated with the connections that you're making. As of course, like timing markers you can set, there's measurements you can take. And this is the dopest part, is that there's like an extension. It's like, I don't know if you guys use Burp Suite that much, but this is like the extender. The extender to Burp Suite is what the extensions are to Logic 2. It's sick. You can create extensions and just basically allows you to have a lot of plugins and stuff. So let's go ahead and swap this guy out. And we're going to look at a completely different device. So this Raspberry Pi is going bye-bye. We're going to put it over there. It's a bunch of pile of other crap I got. And then we're going to switch to the Saleae Logic Analyzer. And then also, we're going to look at this particular device here. So I don't know if anyone on the call right now was at the Rapid7 IoT Village last year. If they were, this will probably look super familiar. So a couple of things. As you can see, we have markings for SPI connection. There you see MISO, MOSI, CS, enable, clock, that kind of stuff. There's also some other stuff here. Disregard this. We're actually only going to use ground. This is for, I believe, an ICSP connection, but we're not going to be doing anything with the Atmel today. We're going to stick directly to the chip, the flash chip, flash memory chip that we have on here. Now, it's going to be an open book situation, but we're also going to pretend like we don't know the pinout of this, just to kind of make it interesting. We do know it, but I'll show you guys how you can probably make that determination, because it's so common that, you know, maybe you'll have like a header pins that are soldered onto the actual vias, or maybe they're only vias, and you have to solder the header pins yourself, and you have no idea what they are. And maybe, for instance, you have a WSON 8. So that means WSON 8, it doesn't have legs. So the flash memory chip, it's like all the solder points are on the bottom, or if it's BGA, those solder points on the bottom. So you couldn't take a multimeter to figure out what the actual pinout is, even if you found the data sheet. So kind of nifty here. I'll show what that kind of stuff looks like. So with that being said, let's just hook this sucker up. This is the part I was telling you guys about earlier, where I'm just like, you're gonna have a good time watching me do this, because there's actually 4 cables. This is double the amount of cables as we looked at earlier. And another little pro tip, actually all 4 of these cables are not required. For doing SPI, particularly if you only have one slave connecting to master, you actually only need to connect master out, slave in, and clock in order to facilitate that connection. But just for shits and giggles, let's just connect them all. Also, I'm going to mooch off the ground interface of this ICSP down here, just to have something. So anyways, very similar to what we saw with the other ones. The mappings of the Saleae are here at the bottom. You can kind of see, it's a little blurry, but my camera is not the greatest quality. Sorry, guys. It goes from 0 to 7, and then the channels are on the top, the ground's on the bottom. You can kind of see there how they're laid out. So we're gonna just kind of start. I'm gonna plug in ground here first. I'm gonna put it in on the far end on this side, and then we'll. I'm cheating a little bit. Remember, you're supposed to pretend, but master out, slave in. I'm gonna make that that 0. So that's red. So we're gonna start red at 0 and kind of work that way. You're kind of picking up what I'm throwing down here. So red, orange, yellow, green, and we need to plug this biatch in. So yeah, the Saleae uses a micro USB. The other cheaper logic analyzers use the mini USB, as you can see there. So we'll grab the micro USB, again hooked up to my computer. Let's plug this biatch in. And you shouldn't see a light. It's totally normal to like not see a light at first with this guy. And yeah, so let's continue on. So let's go ahead and shift the screen over to that side. And we should now see so one beautiful thing is, I don't know if anyone on the call has dealt with Saleae before, but it's kind of a pain in the ass sometimes to deal with a logic analyzer and unplugging and plugging it back in, because you have to like close the software and then open it again. Well, Saleae 2, I had the software already open. As you can see here at the top, it's now connected, the light's on. So I think it's totally dope. But anyways, the Saleae software here, going back to the actual device itself, as I'd mentioned earlier, it supports both digital as well as analog. So as you can see here, here's the digital. So we want to put in 4. We have a total of 4 channels going on right now, and we'll just go ahead and do analog and digital. We'll capture at 10 megasamples per second, and also a couple other things. So there's 3 different ways of capturing with this particular one. There's looping, so loop after a predefined amount of time. There's the timer where it will record for a period of time, and there's a trigger. So just to kind of demo some stuff, let's go ahead and do a trigger. So remember 0. Actually, let's not trigger. Let's just do timer, because we're trying to go black box, right? So let's assume we don't know which particular channel is which, and this is just some blind device that we found online, and we don't know the data sheet, and it's using something like a WSON, so we have no idea like which pin's which. So we have all the channels set up. We have the timer set up for 3 seconds of capture. Go down here. We're going to go ahead and leave the analyzers blank, and we're pretty much ready to start capturing here. So I'm going to grab the old power cable for this guy, and I have it set for 3 seconds. So I kind of need to be quick with my trigger finger here. Gosh damn it, go away Zoom. There we go. So we got full screen. All right, she's plugged in. All right, so we got it. Let's go ahead and zoom out here. Now, this is the capture that we just got, right? And this is during the boot up process. So what you see here is 0 through 3 channel. This is all digital. And on the bottom, it did its best at analog. And the analog, it's not the greatest. Like it's probably pretty accurate. You can kind of see the comparison between the two. Like it tried its best at measuring those voltages, but it probably didn't quite do the greatest that it could. But either way, there's analog. I just want to show you guys some of the analog. That's it's cool to have and stuff like that, but it's not really the purpose of what I'm wanting to show you guys right now. Now, say for instance that you don't know the mechanism of how, or you know that it's SPI, but you don't know which pin's which, right? So whenever we're looking at this device, remember, the top here is MISO, the bottom's MOSI. Channel 0 is master out, slave in. As I'd mentioned earlier, master out, slave in is the information that's basically being transmitted from the actual chip to us. And it's probably going to be a little bit spontaneous. There's a lot of opcodes being set. There's a lot of different various settings being aligned with the actual device. And typically that's one of the first things that'll start communicating, as we can see here. So we zoom in, and a little bit of a telltale thing is that we're starting to see some type of communication taking place right here, a little sporadic. We also see right here, channel 1. Channel 1 in this case is clock. Remember, clock is going to actually set the cadence for how it communicates. 1, 2, 3, 4, 5, 6, 7, 8. It's a full actual byte of data. That's pretty telltale. So right here, of course, channel 0, we have a little bit of some type of like sporadic data being actually set. Channel 1, we have kind of a constant cadence of information being like of the waveform itself. And then enable, what enable is say for instance there's 3 slaves communicating with the actual master node. The enable will tell, it'll flip the bit for when that device can communicate or not. So you'll oftentimes see, and there might be a little bit of a mismatch in our timing, which we can also fix, but you'll often see with the enable that, for instance, right here, there's basically like a 1, 1, 1. There's 3 ones right here. It's going to kind of encompass that entire section, if that makes sense, or cycle. So it's pretty easy to tell if you just kind of scan it as we just did, which one's MOSI, which one's clock, and then which one's going to be enable. Again, enable in our case, channel 2 and 3 is actually not even required. So taking a little bit of a deeper dive, let's take a look at the actual protocol analyzer. We'll click SPI here. Remember, we have MOSI set on 0. We have MISO set on 3. We have clock set on 1. And we have enable set on 2. We'll leave everything else default and we'll click save. Kind of interesting because you can actually find more deeper information about the actual device. And the settings it's applying as it's booting up. Let me kind of scroll in here. Sure I'm not losing my place. So like for instance, like right here, this is the actual decoded binary format. If we go here to the settings, we can change whether it's in binary, decimal, hexadecimal, ASCII, and then take a look at the actual value. So in this particular case, it's like 11001010. And that's the actual location where it made the determination. You can see it up here at the top as well, where it's decoded. And what's kind of also interesting with this is you can take it like a step further and you can pull up the data sheet of the device. In this particular case, the model of this is the MRF49XA. I believe this one was a SOP8. I'm not 100 TSOP8. I'm not 100% sure on that, but either way, it's just an RF flash memory chip. So let's take this code that we got here, 11001010, and let's just copy that. And then let's go back here and let's just paste that in. So I already had it pulled up, so I'm kind of cheating right now. So it's kind of interesting because you can take that, and this is exactly what a developer would do as they're kind of producing these types of devices. They're gonna set these codes, and this is gonna sort of initiate the actual SPI flash storage of the chip. In this particular case, what we saw was 11001010. Let's paste that in again. That's right here. So we see the command code bit right there. And then we can see here below that bit 7 through 4 are the first in, first out, fill bit counts. We have bit 3. So in this particular case, what you want to do is the immediate one below it is you match the next 3 and then map it back over to bit 7 through 4. In this particular, they don't always map like 7, like in a range like that. But in bit 3, for instance, this guy is set to 0. Bit 3, that basically says synchronous character length bit. It's set to word long. So I don't want to continue going down this rabbit hole here, but it's something that's kind of cool to when you're debugging. You can kind of map it back to the data sheet to actually figure out what's going on as far as settings being applied to the chip itself. One other really cool thing I want to show everyone here real fast is we're going to make some changes here. I'm going to go back to the actual mapping of the SPI interface. Pretty sweet. I mentioned earlier, we don't need MISO and we don't need enable. So let's select both of those to none. And let's do something else. This is kind of cool. This is actually a plugin that you can use with this. We're going to select SDMMC from SPI. So this chip, it's not either an SD nor is it an eMMC chip. It's just flash storage. It's not like a solid. It's like an SD actual device, nor is it a multimedia controller. But let's just pretend like it is for a second. You select the input to go into this particular plugin, and then we'll click finish. And if it were an SD or if it were an eMMC, it'd be pretty sweet because up here, as you can see where I'm kind of hovering over, it'll kind of just show you the actual opcodes and the actual information that it's presenting. It'll kind of interpret that for you. So just kind of another sweet feature of the Logic, the Saleae Logic Analyzer software. I just want to kind of show you guys that real quick. And I know we're running kind of low on time. Daryl, are we kind of towards the end right now?
No, we got time for some questions. I have a couple questions here before you move on. So this is kind of stepping back, but do you have to worry about sample rate with cheaper analyzers, like missing data or misalignments and things like that?
Yeah, that's a good question. I'll try to answer that with with a little demo of what that sample rate actually means for the like for instance the Saleae Logic analyzer, which can have very high sample rates. The quick and dirty, the TLDR I'll give you is that for the protocols that we're kind of looking at here, for the most part, the sample rates that these two cheaper guys support are satisfactory for what we're needing. I mean, it's whenever you're diving into the really quick protocols that it really makes like a lot more of a difference, because a lot of times with the really quick sample rates, like say for instance, let's increase this to it's not that fancy of a logic analyzer. It can only go up to 50, but like screw it, let's do it anyway.
Another question on there is similar to that same topic. Is there a general rule on what samples per second selection that you actually make when you're setting something up?
There's not really a general rule. It's more of this is just my own experience. Now, I'm Daryl, you might have your own answer for this, but I would say I typically use it for the default, just depending on what it is. And what I use this for is typically for UART, SPI, and I2C. I would heavily be interested to hear what you have to say.
Typically, I'm pretty much the same way. What I will do is if the sample rate's not high enough, I've actually had my Saleae start throwing errors and tell me that it was missing data, that it wasn't sampling quick enough. I had that just recently looking on some data flow. As soon as I kick it off, man, it'd throw an error and telling me that it was a missed sample rate. So I was able to crank it up until the error went away. So again, sometimes I also just crank it up out of the blue if I know for a fact that it's a high-speed device that's going to be generating a lot of fast traffic. Typically, when you're looking at UART, SPI, and stuff like that, amazingly enough, the speed is often not used as even high as the chip can go. Like UART, I've seen interchip comms on a UART that could literally, the chips are designed to drive at over 3 million bits per second across there. But yet the developers of the device had it set up to communicate at 9600 baud. So
that makes sense. Yeah. And I've also found that if you go too high, this particular Saleae does not support it, but you also don't want to go too high, because if you go too high, what you see right here, get out of the screen, it'll just be a giant blob. It's just a mess. It's capturing too much sampling, and it's kind of just inaccurate at that point. So it's a fine line between the two.
And another quick point on that also is typically the higher the sample rate, the more memory you're going to eat up to.
That's a good point. Are there any other questions?
Not at this time.
Cool. And quick question, I apologize. How much more time do we have here? Just to make sure. I don't want to go too far over time.
I think we've been at it for an hour, so I think we got at least another 10 or 15 minutes.
Yeah, definitely. You can definitely go for another 15 minutes. The next talk starts at 8 p.m.
Perfect. Okay, cool. I wasn't 100% sure on that, but that works out great because we have one more demo as well. So we've talked about, we did a little kind of a cheater exercise on Raspberry Pi. I showed you guys how to sort of blindly identify SPI as well. And then next, let's switch back over to UART in more of a real world example. So let me go ahead and unplug these guys and plug the power first on this guy here. Let's switch back here, make sure I don't bust off any of these header pins live on camera, because this is Daryl's device and it would suck to break it right in front of him. And let's pull over another device. That's going to be this guy. So we're going to stick to the theme with the Saleae. So Saleae is still going to be used. In this particular case, we're going to check out UART, but using the new Saleae 2 software. This particular device, it's a Z-Wave hub, I guess, so to speak. So it's a hub used in home automation. I'm pretty heavy into home automation here at my place, and That's something I've always been like fascinated with. But this particular device, it's a Z-Wave hub, and let's dig right in. So right off the bat, something that can easily be kind of noticed, I guess, is that on this device there was these like three header pins. I soldered the headers on, but previously it was just like 3 holes just kind of sitting there, and that's kind of like telltale that maybe it might be kind of interesting to kind of poke at. It can be anything. It could be I2C. Maybe there's an EEPROM chip on here that's disclosed, or it could be anywhere. It could also like not be on here. And when I mentioned WSON earlier, actually I can't quite tell if this is WSON or actually a BGA, but either way, same difference. Sometimes you can't actually see the legs of the device to where you map it out to, like, say for instance these headers, but rather like sometimes you can, which is what you see right here. This is a traditional TSOP 8. So TSOP 8's got the legs. WSON does not. And I'm pretty sure it's WSON. It might be BGA, but I'm pretty confident that it's WSON. This one for sure is a BGA microcontroller. But either way, sometimes you can't like take like a multimeter to check that this pin right here connects to that pin right there. So therefore, sometimes a logic analyzer will come into play, and then that's where it's usually beneficial to do this type of stuff. So let's move on. Let's plug this sucker in and see what we get. So we only need a couple of connections here. So I'm gonna borrow the cables that I was using earlier for the UART. So in this particular case, there's only 3 connections being made. One thing you can do with this is basically take a multimeter to figure out which one's ground. In that case, let's just assume that I did that because I know which one's ground, but like it's pretty easy to tell which one's ground with just a multimeter. So, and the ground is actually going to be the pin on the far right in this particular case. So let's hook up black to ground, and let's just hook up, white and like this silver one to the other 2, not knowing which one's which. So again, using the handy dandy mappings that we have on the Saleae, we plug that sucker right in to ground. And then we plug in the other 2 to channels, plug them into 0 and 1. Make it kind of easy. And next, let's, you know what? Let's do a trigger. We're kind of gambling right now. We're supposed to be in Vegas right now, so let's do some type of gambling, right? We don't know which ones transmit, but what we're betting on right now is that channel 0's transmit. We have no idea. So let's just figure out that's what it was. And what we're triggering on is a rising edge. And what that says is that whenever you see a rising edge in the transmission in that waveform, that's when you start capturing. So in memory, it's capturing the whole time, but the actual capture that comes back and returns to you is the actual the trigger that you set here. You can trigger rising edge, falling edge, high pulse, or low pulse. In this particular case, let's just say as soon as you see some type of traffic going on channel 1, that's when we want you to capture. And we want you to capture for 3 seconds. Delete everything else afterwards. And we only need 2 channels here, so let's get rid of those other 2. We're gonna leave it at 50 megasamples per second. And that is that. We're not gonna capture on analog. So let's what we're gonna do next is we're gonna close out of that. We're gonna click start. And it's literally waiting for the trigger. So you see down there in the bottom right-hand corner, waiting for trigger. Let's plug this bastard in. Holy shit, we're correct. Yeah, so we still have the stupid MOSI. Let me delete these logic, the decoders. This is my bad. I can get rid of that. And yeah, if we're in Vegas, we basically we bet like $100 on red, and it landed on red because it's exactly what happened here. So go us, right? Channel 0's TX, just as we were hoping for. So that trigger was met and it recorded for 3 seconds. So scrolling into here, we can see some of the data, of course, this is like the 0, 1, 0, 1. And this is a part, as I showed you earlier with the OG logic analyzer, or sorry, the OG logic software. We'll put input channel, we're set to 0, 115200. We don't know what the baud rate is for this guy. I believe it actually is 115200. Remember, we talked about how to check that. But of course, here we go. We're seeing all of the data as well as part of the boot up. So boot, SPL 2017, and just various other information that it's printing out to standard out as it's performing its boot sequence. So anyways, just wanted to show you guys another example of that on the new software here. It's pretty slick. It's totally awesome. I like it a lot. It's super useful. You can see like the parity bits. This is basically the little white dots is kind of managing the communication timing whenever it's sending data back and forth. In this case, it's transmitting. So anyways, that being said, that's kind of the end of the demo here. I just want to give another example of what it means to communicate, or what it looks like to communicate using the new Saleae 2 software. Questions?
Yeah, let's go ahead. I think we have some questions. Let me look at this first. If the Saleae software works for any analyzer, what would be the consideration in purchasing the more expensive offer over a cheaper hardware option shown? So why would I want to buy a expensive $600 logic analyzer when I can buy a $24 logic analyzer, since I could use the software?
Yeah, and that makes sense. So as we talked about, the speeds I don't want to say they're negligible, but you do get significantly higher recording speeds with the Saleae than you would do with the these cheaper versions as well. Another thing too is that the actual accuracy of the protocol decoding, I've noticed is higher with the Saleae than it is with either of these other two devices. That being said, it really just depends on what your needs are. In my opinion, it's pretty good quality. Like for instance, I've had a couple of times where I was doing some type of logic. I was doing basically decoding and actually a live capture, and both I had a crash with the software with both of these devices. So you'll notice that it's a little bit sluggish. It's a little bit rough around the edges. Again, you kind of get what you pay for. The communication, again, there's been kind of like lags and hiccups with these two. They get the job done, but I've noticed that the accuracy for how close of how it captures is a little bit more specific with the Saleae. So if what you're looking to do is going to require you to know those voltages at more of an accurate level, then maybe consider the Saleae versus these guys. I mean, if you're just doing some general like debugging, things like that, I think these are not a bad choice. That's just my opinion. Daryl, do you have anything to add to that?
Yeah, I think accuracy is probably one of the bigger things, and the ability to process at a higher speed. I think are the value, and that's why I went with a higher value product. Because I personally often encounter things that those would not work on at all, just from the fact that it's higher speed. I often get into more inter-chip communication analysis, which is often at a much higher speed than external communication.
Makes sense.
The other question here is a good question. Do you need special hardware for JTAG?
So if you look here, the capability exists for adding JTAG. Actually, does it? I don't know if it does on this Logic 2 or not.
I think it does. I'm not sure.
Yeah, it does.
Yeah,
yep.
There you go.
Yep, I'm sure it does. Now, the question was, is there a specific hardware needed for JTAG? In this case, if you're trying to like identify, what is TMS, what's TCK? If you're trying to identify with JTAG, what are those debug interfaces? You might have the capability of doing it with a logic analyzer. Now, at that point, you're kind of, I don't want to say you're putting a round peg in a square hole, but I don't know if you're necessarily using the right tool. It has a capability of doing it like this, but you might consider using other pieces of hardware for doing something like JTAG. Now, like for JTAG, say for instance, you don't know what the pinouts are and you're trying to identify that. That's where you would use something like, for me personally, I would go after a multimeter first, and I would try to ring it out with the MCU. So I try to find the data sheet and use that data sheet to identify where on the MCU, based off those pins of the MCU, where does that fall out, and use that to identify the pinouts of the JTAG. If you don't have the data sheet, or maybe you don't know where the MCU is, or maybe it's a BGA MCU, then you'd maybe use some type of boundary scanner. A great example of that's a JTagulator. Another thing that you could kind of use the Saleae for is a boundary scanner, sort of. In that particular instance, it could help you, yes. Now, if you're wanting to do something like program an MCU or program the device or upload the device to a flash memory to program an MCU, then you would need some type of programmer, and that's going to be vendor specific. So say, for instance, it's a STM32, you could use something like a ST-Link device. J-Link supports OpenOCD in a lot of cases, so it can support multi-manufacturers. If it's like an Atmel, you want to use like a Picket. So if you're wanting to like either dump or flash some firmware onto an MCU or flash memory, you would use whatever programmer is assigned to that particular chipset. Outside that, you can use a logic analyzer for doing some like limited boundary scanning, but that's kind of not really why it's designed, but the capability exists.
Yep. And on conclusion, there was one comment, or a couple comments in here I thought were funny. One was, it would be funny if someone designed a board with a honeypot header that had 50 volts on it. That's so Jonathan would hook up his $300 logic analyzer and watch it burst into flames.
Dear God, yeah, that would fry the man bun right off my head.
So I thought that was a funny comment, which is definitely the level of evil I would expect from DEF CON. So thank you for that. And then a couple comments saying you did a good job. So that was pretty good. So are there any more questions from anyone as we're getting ready to conclude? Wait, I think there's one more. One was asking more like model numbers on those cheaper ones. Do you have that information? I think those are so generic in nature. You know what I'm talking about, the two cheap logic analyzers. Is there any kind of information on there for acquisition? I think you had a page that actually showed the link to the or information to the actual Amazon site.
Yeah. Let me see here. I'll actually just real quickly do one even better. For like whoever asked the question about that, like Amazon.com, if you like just search like logic analyzer. I mean, one of the ones we're using is like,
I think it was the first one in the list showed up there at the top. Yeah, that's like, one of them. If you go up to the top, I think the first one in the list was one of them we purchased right there. That's one of them. That's the high let go USB one. So
I actually have the other one too. It's kind of funny because it came with the Adify toolkit or whatever. It's like got like a red face to it. I don't know.
Yeah, you may have them called any number of different names.
It's Spark Fun.
Them. Yeah, Spark Fun. Yeah, Spark Fun relabels that Chinese one.
Yeah, it's this one. So I mean, just go online. Really, it's kind of the like here's one of them, and here's the other, and it's just you can just Google or not Google, Amazon search those two. I'm pretty sure this is exactly both of them.
Yep, perfect. Thanks a lot. Let's see. Any more questions? Are hand tech any good? Have you messed with a hand tech before?
Oof, I'm not too sure. Hand tech logic.
Hand tech, yeah.
Oscilloscope or the logic analyzer?
Probably a logic analyzer, since this is a logic analyzer. I have not. Well, you were there a minute ago before you checked on the O-scope. There was one showing up there as a logic analyzer. I could have swore. End in EK, TEK. Because we're quickly running out of time here, but
Oh, I've seen pictures of these guys. It looks, I mean, it's got 2 gigs of DDR2 memory. I mean, that's hella better than I think what any of the Saleaes have. So the quick and dirty real quick with that one, that's a very high sample rate and that's a lot of memory. So higher the memory, the higher sample rate, the longer you can capture and the more pinpoint accuracy you can get in those captures. That's probably, I guess, my 2 cents on that particular one. And it looks cool. It looks dope as hell.
Cool. Yeah, I haven't messed with one, so. Okay, I think that pretty much concludes it. Hopefully the people that wanted to ask questions were able to ask questions. Feel free to reach out to any one of us. Jonathan, you can reach out to him anytime. He's available. I think he's on Twitter. Do you get your Twitter ID out there, man?
Yeah, Twitter ID, Frankensteiner.
There you
Good
go.
luck remembering that.
So if you ever want to ask him any questions or harass him, there you go.
Or yeah, if you want to figure out what my address is, I'll honestly just give it to you if you're really that curious. You don't have to do whatever, Google it or whatever, like the person did at the beginning.
Well, hey, thank you so much. I think there might be a few extra questions. So if either of you have time to jump into the IoTV talk questions text Discord channel, there's definitely people that were pretty engaged with this talk. Despite the technical difficulties, this was our first and only live presentation that had any issues. So, I mean, what are the chances of that? It's like getting a bird pooping on your head. Maybe it's good luck.
Nice. It is good luck.
So with that, we can wrap this up. I'm gonna let everyone know in the Twitch. Make sure to go to the Discord. Hopefully, Jonathan and Daryl will have a little bit of extra time to just talk with you on that channel that we've been linking to. I'm glad everyone had a good time despite some of the issues we had earlier. We're gonna have to cobble together edits of this video from YouTube, just recording my screen. So that will be fun. There might be some blank spots where it's just a question like, what happened here? But yeah, anyway, this was the conclusion of all the Rapid7 sort of like interactive hardware sort of workshop, sort of virtual sessions. I hope everyone found it really fun. I mean, hey, if you guys want to do something again in a couple months, keep some people engaged. I think it would be really cool to partner again with IoT Village, see what we can do, later this fall.
Yep, that sounds like an idea. We'll hit you up on that, Sam. Probably help you out.
Yeah. So yeah, this was been really cool. So yeah, everyone, thank you so much for being here.
Thank you.
All right, Shane, take us off. Jonathan saying goodbye from Las Vegas. All right. So are we all offline? Testing.
The security.
All right, cool. All right, so we're offline from streaming. We're off streaming now.
Okay, cool. I'm going to go ahead and drop this channel, and me and Jonathan will probably jump over to Discord.
Yep, cool. Hey, take care.
Yep, you too. Bye.